Hello everyone. In this video, I would like to provide a guidance to analyze an AC RLC series and parallel circuits. From the analysis, you can sketch the impedance diagram, then apply Kirchhoff's law to derive the formulas to calculate the total impedance using operations of complex number. So take a look at this question number 1. In this particular circuit, the first thing I would like everyone to consider is you want to take a look at the segment inside the circuit. We are going to examine from this node to this node. The purpose is you want to find the two components that are actually connected in series with each other. Alright, so I can identify this as R1 is in series with the inductor, and for this part I can identify it as the R2 is connected in series with this capacitor. Alright, so let's label this one as Z1 and let's label this one as Z2. Okay, so let's go back and review the concept of mathematical models that representing this type of circuits. So let's go back to the previous handout that I provided for everyone in the previous lesson. You see that you want to find the impedance for the two components that are connected in series with each other in terms of the phasor, right? So R is always the real part, which is your resistor, but the inductive reactance will attach to the positive part of J. If you add these two vectors, you will find the resultant vector, which is the total impedance for these two components. Alright, so if you are working with a resistor connected in series with a capacitor, then the impedance in terms of rectangular form, R, your resistor, will be the real part of this rectangular complex number, and your capacitive reactance will take on the negative part of J and will become your imaginary part of this complex number. They act as vector, so if you add these two vectors, you will find the impedance for these two components connected in series with each other. Okay. So let's get back to our handouts. For this type of circuits, the best is to analyze each of them individually, and then from Z1, Z2, you are going to draw your impedance diagram. Okay, so drawing the impedance diagram, I will have is like this. Okay, so right here is my Z1, right here is my Z2. So now you realize that Z1 is actually parallel to Z2. Given that we know the basic Ohm's law, basic Kirchhoff voltage law, and also basic Kirchhoff currents law, so I can review a bit for everyone here. Alright, okay. So if you generate the currents going through this circuit, right at this node, it will split into two. Okay, it will split into two. As soon as you see the current split into two, the components in here will be parallel to each other. So if they are parallel to each other, in terms of impedance and measured in ohms, their formula is supposed to be like this. So you find 1 over Z total will be equal to 1 over Z1 plus 1 over Z2. Alright, so I will simplify this for everyone, and to show you that it's a product over the sum. As I indicate in previous lesson, I say that is the product over the sum, right? So you take Z1, you multiply with Z2 over Z1 plus Z2, and this is your Z total. Don't forget the product over the sum only applies for just two impedances in this case. So that is a good idea that I should go over the algebra behind this, that how we can get into this product over the sum. Alright, so I have to find the common denominator in this case. Okay, finding the common denominator in this case, I need to multiply this with Z2, I need to multiply this with Z1. Alright, so in this case, I will have Z2 plus Z1, the whole thing divided by Z1 times Z2 as a common denominator. So for me to solve for Z total, I will have to flip this fraction over as well. So now I will have a product over the sum. And it doesn't matter if I write Z2 plus Z1 or Z1 plus Z2. It's the same thing according to commutative rule in algebra. Alright, okay. So don't forget, I use product over the sum because most of the time I'm working with just two impedance and they are in parallel with each other. As soon as you have three impedances and they are in parallel, and then don't use product over the sum, but you have to analyze and finding the Z total using these formulas. Alright, okay. So let's go back and review what is Z1 equal to. Okay, Z1 will be equal to R1, and you are adding that with the positive part of XL times J. So Z2 will be equal to R2 subtract the capacitive reaction times the J. Alright, okay. Let's move on to the next question. So this circuit is just the two components in parallel with each other, but the next one you may find that you have the combination of series and parallel. Alright, okay. So again, the same concept. We are starting from this and stop right there. And this is one components for the impedance. So I label that Z1. So this will be my Z2. Okay. And this will be my Z3. So let's write what Z1 equal to. Okay, so the Z1 in this case will be equal to R1 plus XL1 times J. So Z2, you don't have any R in this case, so you can put a 0. You plus that with XL2 times J. So Z3 will be equal to R2 plus a minus of, I write it in terms of vectors here, okay? So the XC1J, so therefore is R2 subtract XC1J. Alright, okay. So analyzing this and draw the simple impedance diagram. So this is my Z2, this is my Z3. Now you see that, excuse me, Z2 is parallel to Z3. So because you only have two in this case, so you can write it as the product over the sum. So this part here will be Z2 times Z3 divided by Z2 plus Z3. Don't forget, this product over the sum only applies for two components that are in parallel. Then if I draw another simplified diagram, so here is my Z1, and here is already Z2 parallel to Z3. Now you see that Z1 is now in series with Z2 parallel to Z3. So basically, your formulas to find the Z total in this case will be Z1 plus your product over the sum of Z2 and Z3. Alright. Okay, so let's double check. I think everything looks good. Okay, and up here also everything looks good. Alright, so let's move on to the next question. The next question is very much similar to number 2, so I will quickly go over this, except that this part of the circuit here, I only have the capacitor to work with. Okay, so again, Z1 is equal to R1 plus XL1J. Z2, again, you want to write a 0, subtract XC times Z. Okay, and R3 will be equal to the R2 plus XL2 times J. Alright, okay, so very nice. Excuse me. So now we are going to draw our simplified impedance. So here Z1, Z2, Z3, connect it back to the source. So now you realize that Z2 is parallel to Z3. Okay, so similar to the previous questions, I can apply product over the sum for these two because I only have the two components in parallel to each other. So Z total will be equal to Z1 plus Z2 times Z3 divided by Z1 plus Z3. So what you do in this case is now you can perform the operation of all of this complex number using polar form when you multiply. If you divide, then using polar form to multiply, divide, using rectangular when you add or subtract. Alright, so I provide everyone with the final answer right here and round to 3 significant digits. And to get these 3 significant digits, I actually use 4 decimal places in my calculation so that we will be consistent and we maintain the more precise for our significant digits. Alright, so I would like to move on to question number 4. Okay, and the same thing here. Will be this as my Z1, this will be as my Z2, this will be as my Z3, okay, and the same approach, simple diagram, alright, okay, and again, this two, I can use the product over the sum, and then my Z total will be equal to Z1 plus this 2 parallel to each other. Right, okay, so let's double check. Okay, so double check, I think we should be okay. Everything looks good. Okay, so don't forget that this part will take a negative part of J, this one will take a positive part of J, and also we take the positive part of J there. Alright, okay. And it's C1 plus the product over the sum of these two parallel to each other. Okay, so that is right there. Okay, so let's go on to this question number 5. Okay, so with this question number 5, what I have is this part here. I will label it as Z1, this as my Z2, this as my Z3, and this as my Z4. Okay, so the simplified diagram will look like this. Z2, Z3, Z2, Z3 are parallel to each other and now connected in series with the Z4 and go back to the source. Okay, so another simplified diagram would be like this. So here's my Z1, this, you already make that into Z2 parallel to Z3, which is the product over the sum. And here's your Z4. So therefore, you see now is all of this in this circuit, run the current through it. It doesn't split anywhere, so this will be in series. So that means you have Z1 is in series with Z2 parallel to Z3, which you already found as product over the sum. Okay, and this part is series with Z4. Therefore, your Z total in this case will be Z1 plus Z2 times Z3 divided by Z2 plus Z3 and plus Z4. Alright, so it's looking pretty good. Okay, so now you see that the mathematics will in fact simplify this circuit. It looks quite complicated, but if you analyze it in terms of phasor, in terms of individual impedance, connect them again in a circuit to recognize they are in series and parallel, draw these formulas out of that circuit and your analysis. And all you have to do here now is to substitute the value in for Z1 in terms of rectangular, Z4 in terms of rectangular, and your Z2, Z3 rectangulars but convert to polar form as well. And all you have to do is just perform order of operations for complex number. Alright, thank you.